Okay, so in this video we're now going to talk about the idea of choosing the integral representation that works best for the problem that you're actually trying to solve. And the way I want to do that is to sort of show you different choices you could make for calculating the same physical quantity. So let me sort of do a setup first. The physical quantity I'm interested in calculating is I've got this chef's knife, right? There's the chef's knife. If I look at this chef's knife from the sort of front on and sort of turn it, right, there's a sharp edge of it, and obviously as I go down along it, that sharp edge continues down to a sharp point. So sort of a complicated shape, and I'm interested in knowing what's the mass of the blade of this knife. Well, there are a couple of ways I could think about doing that. One way I could think about it is what we've just sort of thought about, and I could say, okay, well, the mass is actually simply the integral over this domain, right? Or I'll say the domain is the blade of a differential mass element, and I'll get more explicit about that. I'm going to write that as a three-dimensional integral over the domain, and now let me draw that domain, and or at least attempt to draw the domain in sort of cross-section. So I'm exaggerating the sort of size of these triangles, but sort of here's what the knife blade looks like if you kind of blow it up, right? So I've got, if I sort of create my coordinate system here, let's make this x, this y, and this z. So you can see I've got this sort of region that's defined in x, y, and z. And I could think about dividing that region into little chunks and saying, okay, well, that region consists of a bunch of little chunks, dx, dy, dz, right? Each little chunk has a volume, dx times dy by dz, and the mass of that little chunk is whatever the mass density of this metal is, presumably it's carbon steel or something. So mass density of carbon steel times dx, dy, dz integrated over this domain. And I could go even further and write the definite integral for this. So let's think about what that definite integral is. Pretty clearly y is going to vary between, say, 0 and L, right? There's some length to the thing. So let's say y is going from 0 to L, right? So I'll have dy as my outside element. X is going to run from some negative thickness to some positive thickness. So x is equal to minus t, and t depends on y, to plus t of y, right? And then z is actually going to depend both on what x and on what y is, right? So z is going to go from 0 up to some height, right, where the height is some function of both x and y, right? And I need to figure out what this function t was as a function of y, which tells me how wide the blade is. I'd also need to figure out this function h, which tells me how high the blade is at any given xy coordinate, right? So that's the one way that I could do that. And another way that I could think about it is actually to say, you know what, I'm going to think about this not as a three-dimensional domain. I'm actually going to think about it as a two-dimensional domain. So here's my two-dimensional domain, right? This two-dimensional domain is only defined in, say, x and y, right? So I've just changed my coordinate system. I'm going to define it differently. And for that two-dimensional domain, I have to ask the question, what's the area of one of these chunks, and how much does that chunk, what's the mass of that chunk? So I'm going to be doing a double integral over this domain, I'll call it d prime, of a surface density, right, which is kilograms per meter squared times dx dy. Now, of course, that surface density is going to depend on what the thickness is as I go further up, right? So I'll need to actually have some function that tells me what this sigma is, and that sigma is going to be the density times some thickness, which I will call t, which depends both on what x is and also on what y is, dx dy, right? And again, I would integrate from here to here and then from here up to here, so same type of game. But notice that what I've ended up doing is frame the problem differently by choosing to integrate over a two-dimensional domain instead of choosing to integrate over the three-dimensional domain. When I chose to integrate over the two-dimensional domain, my integrand became more interesting, right? Here my integrand is 1, or is row, I guess I should say, right? Here my integrand is row times some function of x and y, but I should get the same answer, right? And I could even go one step further and say, well, actually, let's think about this as a one-dimensional problem, right? So now I'm just going to integrate with respect to x from x equals 0 to x equals L, right? But now what I have to do when I'm doing that is ask the question not what is the, I'm asking a question rather not about how much mass is contained in each little chunk. I'm instead asking the question how much mass is contained in an entire slice, right? So I would actually do the integral from x equals 0 to x equals L of the linear mass density, right, which would be the kilograms per meter of the knife, which depends on x, times dx, right? And so conceptually what I'm doing when I do this is I've got my knife, right? And I could think about what the mass is, what the differential mass is of each one of these chunks, and I'm adding up each of those differential chunks as I move along x, right? So I've actually got 3 different ways that I could choose to do this. Notice that effectively in this one-dimensional case, what I'm doing is integrating some function lambda of x, right, which is going to look, something kind of like that, but probably more extreme because there'll be more mass on this side than on this side because it'll be thicker here than here. Or integrating some function over 2 dimensions in this case, or simply integrating a constant over 3 dimensions. You should get the same answer either way, in any one of these 3 ways, but they're 3 very different ways to think about the same problem.